All right, so today we're going to do something a little different. We're taking a physics test, but we're not just looking for right or wrong answers. We're going to treat it like something way more interesting. What if, every single question wasn't just about getting it right, but was actually a clue, a key to unlocking one of the universe's fundamental rules? Well, that's exactly how we're going to approach this thing. So let's just dive right in and see what secrets we can crack open.
So here's our source material. It's a practice test, right? For folks hoping to get into med school in India. It's just jam-packed with questions on mechanics, heat, thermodynamics, the works. But here's the twist. We're not solving for X. Nope. We're solving for understanding. And we're going to start small by decoding the secret rules that run the hidden world of liquids.
Okay, first up, the secret life of liquids. And this stuff it's kind of weird and wonderful, right? These are forces you see playing out every single day. I mean, every time you see a raindrop or blow a soap bubble.
So this question about a soap bubble, that's our way in. It asks about pressure. I mean, why is there extra pressure inside a bubble anyway? Well, it's all because that liquid film, that skin of the bubble, is constantly pulling itself together. It's trying to shrink. And that inward pull, that's a force we've got to get our heads around.
And that force has a name, surface tension. It's the reason water forms little spheres, why some bugs can literally walk on water. And think about this. It actually takes energy, or what physicists call work, to stretch out that liquid skin. That's a huge concept that pops up again later. But the big takeaway for now is this. Liquids have this invisible skin, and it's always trying to pull inward. Okay, so that naturally leads to another question, one I'm sure you've thought about. Why is it that water spreads out flat on, say, a clean piece of glass, but on a waxy leaf it beads up into a little dome? Well, our codebook, it's got the answer for that one too.
And honestly, it all comes down to one simple thing, what they call the angle of contact. Look at the left side here. When a liquid is more attracted to the surface it's on than it is to itself, it just spreads out, right? Makes a really small angle. But on the other hand, when it's more attracted to itself, it pulls inward into a little bead, and you get that big angle on the right. It's pretty amazing, really. It's like a tiny cosmic tug of war happening right in front of us.
All right, so we've looked at the forces inside liquids. Now let's kind of zoom out and tackle the energy that gets literally everything moving in the universe, heat. Okay, I have to admit, this next question is one of my favorites. The scenario is just wild. Imagine a block of ice falling from so high up that it melts completely, just from the energy of the fall itself. I mean, wow. It's the perfect example of how the energy of motion can turn directly into heat. So the big question is, just how high does it have to fall? Get this, 68 kilometers. That's what, almost 8 times the height of Mount Everest? It's just an incredible way to show how much energy is actually locked away as heat. To think that falling from pretty much the edge of space is all it takes to turn a solid block of ice into nothing but a puddle of water? Mind-blowing. So, okay, we've got all this heat energy. Now what? What does it do? How does it even get from point A to point B? From the sun all the way to Earth, or from a hot stove to your hand? Well, our codebook breaks down the 2 main ways it travels. So on the one hand, you've got conduction. That's just heat transfer through direct touch. Think about question 12, where heat flows down a metal rod. Simple enough. But then you have radiation. That's heat traveling through waves, like the energy we get from a star. It's really just the difference between, touching a hot pan versus feeling the warmth of a campfire from way across the yard.
Now, to really get radiation, physicists came up with this idea of an ideal black body. And the text gives us a fantastic definition. It's not just, something painted black. The key is that it's a perfect absorber and a perfect emitter of energy, kind of like a cosmic sponge for radiation. And the best real-world example? It's actually a hollow box with a teeny tiny hole in it. Any light or radiation that goes in just gets trapped.
So how do these things like stars actually give away their secrets? It's simple, through their color. There's this rule called Wien's law, a super important part of our codebook, and it says an object's temperature dictates the color of light it shines brightest. So as you can see here, hotter things glow bluer, while cooler things glow redder. It means we can look at a star trillions of miles away and know its temperature just by looking at its color. Amazing.
And it's not just about the color, it's also about the sheer power. There's another rule, Stefan's law, and this one tells us that the total energy an object blasts out depends on its size and, this is the crazy part, its temperature to the 4th power. What does that even mean? It means if you double the temperature, the energy output doesn't just double, it multiplies by 16 times. So the main takeaway here is really simple. A little bit more heat means a whole lot more energy. Okay, so we've got this incredible source of energy. Awesome. But what do we do with it? How can we use it? Well, that brings us to our final section, putting all that heat to work. And this little phrase, pulled right from a question about an engine, gets right to the absolute heart of thermodynamics. It's all about the science of taking messy, disorganized heat energy and channeling it, converting it into organized, useful work. You know, the very force that powers everything from old-school steam trains to the car you drive every day. So how does it actually work? Well, just think of it like a simple four-step dance. First, the engine sucks in heat. Second, that heat makes a gas expand and push a piston. Boom, that's the work getting done. Third, it gets rid of the leftover waste heat. And fourth, it squeezes the gas back down to get ready for the next round. Absorb, expand, reject, compress. That's it. That's the simple rhythm that literally powered the Industrial Revolution. And here's the cool part. Physicists don't just talk about this stuff, they draw it, they map it out. These diagrams from questions 30 and 31, these are called pressure-volume diagrams. And they're basically the blueprints for an engine. See that area inside the loop? That's the actual real work you get out of every single cycle. It's a way to turn this whole abstract process into a simple visual shape. And holding this entire idea together is a rule so important, so fundamental, they just call it the first law of thermodynamics. And the core idea is actually super simple. You can't get something for nothing. There's no free lunch in the universe. Energy can't just be created out of thin air. It can only be moved around or changed from one form to another, by adding heat or by doing work. Okay, so let's zoom all the way back out. We've looked at liquids, we've looked at heat, and we've looked at engines. So what is this little physics test, this universal codebook, actually taught us? Well, for one, it's shown us that these invisible forces, like surface tension, are literally shaping the world around us. We learned that heat isn't just about how hot or cold something is, it's this incredibly dynamic energy that can be born from motion and can travel across the empty void of space. And maybe most importantly, it's shown that once we understand these rules, we can actually build machines that harness that heat and turn it into real useful work. And that is the real takeaway. These aren't just tricky questions on a test. They're not just some academic exercise. They are little windows into the operating system of the entire universe. The same basic principles that decide the pressure inside one tiny soap bubble are connected to the very laws that govern the immense power of a giant star. It's all connected. So yeah, we've cracked a few of the universe's codes today. It just makes you wonder, doesn't it? What other secret codes are still out there, hiding in plain sight, just waiting for someone to come along and ask the right question?